let's continue on with this notion of lumped element matching by considering what's known as an L section. So the book gives two different types of L sections. One is called the high-low, and the other is called a low-high. So you can see it starts in series to parallel or parallel to series. And by L section, you can see, use your fingers here, so there's an L and then another L that way. And we have some load here that is mismatched to the characteristic impedance. So we're going to write this out here. Z sub L is equal to R sub L plus J X sub L. And this is mismatched with my characteristic impedance. So somehow I would like to insert little components of just inductors or capacitors to try and match the impedance here with this load. So you saw in the earlier sections, or the earlier lectures, where if we matched the real part, all I had to do was insert, say, some appropriate reactance to balance out the other term. But that was only true if the real part was matched. So if I have both a mismatch in the real and the imaginary, then that's 2 degrees of freedom, which means I'm going to need 2 different components here to create that match. And as it turns out, if I have a mismatched real and imaginary, all I need are 2 reactive elements here, placed in the appropriate values and configuration to create a real and imaginary match. So you can think of it as there are 2 degrees of freedom here. So I need 2 degrees of freedom over here. But what's neat is there's no real loss in these terms here. So I'm actually still getting all of my power to go to the load without any loss of efficiency in these reactive elements, at least in principle, right? Because any real element will have some intrinsic loss, but ideally it'll be very small, which means you can get a very strong match. So the conditions for these, the high-low versus the low-high, they are not entirely interchangeable. So what we're going to do is first we're going to calculate a normalized impedance. So that's a little ZL, not to be confused with a capital ZL, which is capital ZL over Z naught. And now we're going to plot a Smith chart here. So something like this. 1, 2, 3, like here. 1, 2, 3, 4, 5, say. And then we'll draw an x-axis over here. 1, 2, 3, like so. Okay, so imagine here is my unit circle on my Smith chart. And 1, 2, 3, oops, I made that a little big. Here we go, do that. Sorry about that. So I'm going to draw that little reactance circle here, like so. So remember, this corresponds to a reactance of 1 plus Jx kind of thing, right? So if I have a real part that is matched to my load, but my imaginary is mismatched, then that will be somewhere on this circle. So you imagine this little shaded region here. So for the special case of, let's see, it is in the book here. It specifically says you have to pick one over the other. So for the low-high, here's the high-low. It has to be inside. So you can think of inside this circle is a condition R sub L is greater than or equal to Z naught, right? So remember, short circuit is over here, open circuit over here. So if I have some reactance with a high real part of my impedance, I will land somewhere inside of this circle, and this will correspond to the high-low. Okay, and if I am somewhere outside of that circuit, out here, okay, so that implies my R sub L over here is less than or equal to Z naught, then the appropriate network will be the low-high, like so. Okay, so you notice they're not interchangeable. Depending on where you land in the unit circle here for my Smith chart, that will determine which network is the appropriate one to utilize for creating a match. Okay, so let's suppose I figured out my load and I plotted it somewhere on this unit circle. Let's say, let's do the first case here. And suppose hypothetically my reflection coefficient lands here. That is for the unmatched load. What exactly do I have to do over here to create the matched load using nothing but these reactive elements? And the book kind of gives two different explanations. They're technically two perspectives on the same result, but one is kind of a graphical interpretation, and the other is just pure algebra. So graphically, remember that when I put an admittance over here, so ignore this term here. If I added an admittance, that corresponded to motion along a circle in this direction. So let's grab maybe a different color. So I'm going to draw an admittance circle, maybe kind of like that. And so the center will be up about here, and it'll do something like this. There, so that is an admittance circle. And if I add or subtract, or if I put a positive or negative admittance into this term here, that will correspond to a rotation along this circle of that little x point, right? So hypothetically, I could move it all the way up to here, or I could subtract with a negative value and move it the other way. But what I want to do is I want to add just enough so that it lands right here on that little tip of this reactance circle here, the 1 plus j something there. Okay, so you notice I can dial this knob however I want, and I just want it to land here. And then what I'm going to do is add this series reactance here, which again, remember, corresponds to motion along this circle in this direction, as we saw in the previous lecture. So just from a purely visual perspective, you can look at this reactance or admittance term here as moving up along the circle until I intersect with the green circle here. And then I add the series bit so that it starts moving back along there, and I add just enough to create a load. So in your mind, it's very important to associate these two reactances with motion along these circles inside of the Smith chart. So then there's the algebraic response, which we'll get to, and we'll also do the opposite case over here. But you notice I could also put a negative value here, which will move me in this direction, and potentially I could land on this point of the circle, and then I would put the appropriate reactance over here, and I can come up. So one of the beauties of this, these L-section networks is there's actually two solutions between these two reactances that will get me a matched load. I can either go up the circle and then come down, or I can go down this circle and then come back up. So let's now look at the opposite case here. So I need to quickly draw yet another Smith chart here, and you can see the imprint from my previous lecture. So let's do that real fast. Okay, so here is yet another Smith chart. So we'll move it over here. And let's suppose hypothetically we're in this case here. So we have this circle, which we drew. So our first case, we landed somewhere inside of that circle. What if hypothetically I land somewhere outside of it, like over here? Now what do I do? Well, you just imagine in your head, here is the opposite admittance circle here, okay? So what I would like to do is somehow get that x to land somewhere on the edge of this circle here. Okay, so what you imagine is there is another circle, an impedance circle, that kind of looks like this. Maybe it goes about there, and it comes down right here. So I'm going to draw this, a little continuous, like so. So there's where I am. And if I add a series reactance here, either positive or negative, it will either go that way or that way along that blue circle. So all I'm going to do is add the appropriate reactance here until I either intersect here, or I can keep going and maybe intersect over here. Because again, there are going to be two solutions. And then this little bit of reactance here, the admittance here in parallel, will again take me up this circle here. So you notice the opposite was happening. First, I went up the admittance circle and then came down an impedance. Now I'm going to go down the impedance here and then move along the admittance until I arrive at a match load using nothing but passive components here. So that is kind of the graphical interpretation of what's going on based on the discussions we had in the previous lectures. So that works pretty well, and you can use Smith charts without even touching a calculator to get appropriate values here. But for this class, I think it'll make the most sense because we have access to MATLAB to use MATLAB as the actual number crunching machine. But it's going to be very important to kind of still have that connection to the visualization of what's happening in terms of Smith charts. So I will create a couple of homework problems where you kind of just trace the motion along the Smith chart to see what's happening. And what you'll see is I add series or parallel reactances here. You'll follow a circle and then you'll stop and then you'll follow another circle again to get to the matched load. So again, that's the visualization. So in the next lecture, we'll talk more about kind of the algebraic solutions instead.